Okay, so let's now move on and start to talk about how gravity works when we don't have to worry about individual collisional interactions between the bodies, right? So this is now collisionless gravitational dynamics for large systems where the time between collisions is very long. So we still have, objects that are exerting a gravitational force. They exert a gravitational potential, and we'd like to know how things move under the influence of that potential. The actual details of the dynamics is very similar to how we dealt with electric fields, right? There's a Gauss's law, and there's a Lorentz force, right? In electrostatics, we talked about the confluence of those two terms, and there's really an exact same version of those for gravity. You have a gravitational field, which tells you about how something exerts a gravitational force. Then the force on some object depends on that object's mass, just like the Lorentz force depended on that object's charge. There is the difference of the minus sign in the gravitational Gauss's law, of course, because if you had a positive charge density and a positive test charge, they would have a repulsive force. But we know that we have density, mass density, and masses that are positive definite. That generates an attractive force. So yes, minus sign. We can write the field as a gradient, as minus the gradient of a potential. And thus, when you plug that back in, you get Poisson's law for gravity and for the electrostatic field, which we didn't talk much about. But the Laplacian of the gravitational potential is just proportional to the mass density with other factors. And of course, this is now true when you want to evaluate the potential at some region where there's stuff, right? If we're in the galaxy and we want to know how the rest of the galaxy is affecting us, both sides of that equation are going to be non-zero. The simple version is if all the density is over here and we want to evaluate something way out in a vacuum over here, then that right-hand side is going to be zero, and it's essentially Laplace's equation, right? Laplacian of the potential equals zero. And we dealt with that when we looked at magnetic fields. And essentially the solution is to take that gravitational massive stuff and expand it in terms of multipoles, right? The further away you go, the fewer number of multipoles that you need to talk about the gravitational forces. So yeah, but in general, we'll be talking about being embedded within the galaxy, say, and we'd like to know how Poisson's equation works. Whoops. Now, if you know the density distribution, you can solve for the gravitational potential. It's a differential equation for the potential in terms of the density, but you can do it. On the slide here, I have various pieces of text talking about Green's function methods or Gauss's divergence theorem. It's just a way of sort of solving that differential equation for phi in terms of rho. And, we've seen this before. What it really looks like is Newton's universal law of gravitation, right? Minus g times a mass divided by a distance, minus gm over r. That's what it would be for a point mass. And that's also essentially what it is for distributed mass. You just have to add up all those little distributed pieces and do, that ends up being an integral. Right, so we're going to talk a bit about spherically symmetric distributions as a first sort of idealized case. And then later on, we'll talk about axisymmetric, sort of squashed systems where sort of like the galaxy, it's a disk, right? Where it's still axisymmetric in phi, but it's squished in z. But we can start with spheres. That's a sort of a simpler thing. Spheres are particularly nice because this integral over volume and density boils down to just a single integral over r, right? The theta and phi directions are all symmetric. That's just 4 pi, and you just have r squared rho dr. And what we can do is define this differential quantity here on the right as just a differential amount of mass, right? It's essentially the mass in a thin shell, spherical shell of width dr. So if you wanted to calculate how much mass is interior to some radial distance, you just sum up all those little dm's from r equals 0 out to r, the r that you want to calculate it. Yeah, I guess we can talk. I mean, we can talk about this in different ways. You know, you could show that the dm and the rho times 4 pi r dr are really the same thing, just two ways of writing the same thing. How much mass is contained in this shell? If it's a really thin shell, then you can assume that it's got a constant density. So you just need to multiply the density times the volume of the shell. If it's thin, it's just the surface area times the thickness. And there you go. And in stellar interiors, you can put these two things together and form a differential equation for the mass interior to some radius r in terms of the local density. But here we're just going to be talking about summing it up, you know, basically performing this integral over this mass coordinate or the radial coordinate. Yeah, and so now why do we care about the mass interior to a given radius r? Well, Binney and Tremaine go on to talk about two theorems of Newton, and I'm not too clear about whether these first and second theorems are as well known as the three of Newton's laws, but people like to enumerate the things that Newton did. But now there are these two ideas about how is a spherical shell of mass going to affect some test point somewhere else in space. If you're inside that spherical shell, it turns out that the net gravitational force due to the shell is 0. And I'm sure you've done this calculation before, right? If you're exactly at the center, of course, everything cancels out. If you're off to the side, yes, you're nearer to one side and there's more mass over here that might attract you. But over on the other side, further away, there's a lot more, maybe per solid angle. There's a lot more stuff over here, even though it's further away. And that cancels out exactly no matter where you are. So yeah, if you're inside the shell, the force is 0. If you're outside the shell, the second theorem says that if you want to calculate the gravitational force of the shell, it's all symmetric, and it's basically the same force as if you take all that mass and you concentrate it into a point at the center. So that second theorem is really the one that tells us that all you need is the single scalar number, how much mass is interior to where you are, and that's really all you need to know to figure out the force on some external object. Right, so if you wanted to figure out the gravitational acceleration on some point, that's just minus the gradient, the r gradient, if it's spherically symmetric, of the potential, and the result just ends up being minus gm over r, where that m is how much mass is interior to where you are. Now, it's kind of strange, but if you wanted to write out the full potential, not just the force, the potential depends on both the mass interior and exterior to where you are, but the actual force on you doesn't. So maybe there's a point in the column of working with forces rather than potentials and potential energies. The example that the simplest example that I can think of for this is a constant density sphere. We sort of touched on this a little bit when we talked about the potato problem, because you would need to sum up quantities like this to figure out the gravitational force and the pressure as a function of distance for this simple constant density model. If density is constant from 0 to capital R and then 0 outside, the mass interior to a shell, if you remember, maybe I should go back, the dm has an r squared times dr. So if the density is constant and you pull it out of the integral, you integrate r squared, you get r cubed. Oops. And that increases from 0 at the center, right? There's no mass interior to where you are at the center, to some maximum value at the surface. And then at all larger radii, it's constant, because even though you're going to larger radii, there's still the same amount of mass interior to where you are. And then you calculate the gravitational potential. In the interior, it's got this strange quadratic shape, but it's sort of flat and finite at the center, unlike a point mass, whose potential diverges to minus infinity at the center, right, at the point where the point mass is. But above the surface, it works out to just be sort of point mass-like, right? It's just a -1/r potential that drops off, as if all that interior mass was concentrated at the center. But when you're evaluating it in the interior, it doesn't look like that, right? It's something else. It's something more gentle. So when people try to figure out what are the potentials of extended systems like galaxies or molecular clouds, there's still some central condensation, but there's still extended gas throughout the whole thing. In some ways, you would like it to act like that constant density model in the inner regions, but then in the outer regions, it's fine if all the mass is sort of interior to where you are, and it sort of acts like a point mass. So people have looked for sort of continuous functions that bridge both of those limiting cases. The first one was found, now more than 100 years ago, before we even really knew what the galaxies were. But Plummer worked on this function that essentially, in the limit of large r much bigger than this factor a. This is just minus gm/r, right? Point mass. But when r is of the order of a or less than a, it's a much more gentler, flatter type of a function. And then when you use Poisson's equation to calculate the density that is consistent with this phi, it's a function that is also similarly flat for small values of r, right? If r is small, this is just 1 plus epsilon, a small number, so it's mostly a constant. But when r is large, this goes as r to the -5. So essentially, r is dropping off continuously, but very steeply at large distances. Yeah, so these types of functions are used a lot as sort of fitting functions to map galaxies when you can get some measure of either the density or the potential as a function of distance from the center. Another one was worked out by Henon in the 1950s. I'll have a link to a more detailed historical deep dive into why this is called an isochrone potential. It's slightly different. It's similar but slightly different to Plummer's model. There's this extra constant, and it turns out that when you churn it through Poisson's equation, rather than density to the -5, it goes as density to the -4 at large distances. So small little factors can make big differences to the functional dependence of these things. When you study dark matter halos, oftentimes what's done is to go in the opposite direction. You start with the density and then use that Green's function or Gauss's divergence theorem expression to compute the potential. And this sort of popular family of functions is often used. And there's a whole bunch of different papers that refer to them. NFW stands for Navarro, Frank, and White, who worked this out in the 1990s, and it's still a popular version. But yeah, so these dark matter halos are usually close to spherically symmetric distributions of something that's exerting a gravitational potential on a scale bigger than a galaxy. It's not always exactly spherical, so in future videos, we'll be talking about non-spherical but axisymmetric models. So we'll be using these spherical coordinates, and apologies for changing the notation. This is Binney and Tremaine's notation for cylindrical coordinates. This capital R is now the horizontal radius, the x squared plus y squared square root distance from the axis. But here we're now going to assume that the density and the potential don't depend on phi, but only depend on r and z. And yeah, our end goal here is to figure out what is the behavior of density and potential in systems like our own galaxy that we're sort of in the middle of. And it turns out that looking at the motions, looking at the orbits of individual stars under the influence of these potentials is going to be the key that opens the door to figuring out what these things are.